Hello and welcome to the video lecture on the chemistry of heterocycles. In this installment, we tackle the problem of the retrosynthetic analysis and synthesis of the pyridines, quinolines and isoquinoline ring systems. Only those name reactions will be discussed which are in our syllabus. So we take the case of pyridine and we do a retrosynthetic analysis by adding one hydrogen here at the nitrogen and at the gamma carbon or the C4, one hydrogen here and one hydrogen here. So basically in this case, in the forward reaction, we are looking for an oxidation, and then we add one element of water, hydrogen here and OH here at the C2OH and at the C3H. So in the forward direction, we are trying to convert this to that, therefore we are looking for a dehydration. Now we have a carbon which is a one difunctionalized carbon, so we do a HOCN disconnection and cleave the nitrogen carbon bond here. So we end up with an amine like fragment and a carbonyl here. So in the forward direction, we are looking to close down the ring by attack of the NH2 to the carbonyl carbon. And now we have 1, 2, 3, 4, 5, 1, 5 di-X relationship. So we can disconnect it here, and therefore we end up with the enamine and also an enone. The enone represents A3 synthon because here is the positively polarized carbon with respect to this carbon. So that's a acceptor synthon, enone, and this is a enamine. Therefore it is the 2, this is the 1. Therefore this is a nucleophilic center, an enamine. Therefore it's a D2 synthon. The bare bone skeleton structure of these synthons are like that, where you have the del plus charge here and here. So it's a 1,3 dipolar kind of thing, 1,3 electrophile, and here you have a 1,3 nucleophile. Nitrogen is also nucleophilic, and also the this vinylic carbon of the enamine. So the enamine can be thought to be coming from the corresponding reaction of the carbonyl compound and ammonia, where we have the tetrahedral intermediate which loses a water molecule from here and we get an enamine here. And the enone is obviously coming from a aldol type condensation between an aldehyde and a corresponding ketone. So you need a cross aldol type reaction. So the mechanism of this reaction, this is the approach which Hantzsch took in synthesizing its pyridines. And this is known as the Hantzsch pyridine synthesis. So he took the aid of two active methylene compounds and condensed it with ammonia with an aldehyde. So the very first thing that can happen is that it forms an enamine with one of these. This ammonia forms an enamine with one of these active methylenes, whereas in presence of the aldehyde, the other active methylene undergoes a Knoevenagel condensation, where the same ammonia acts as a base and forms this alpha beta unsaturated carbonyl compound, the enone. So we have our D2 synthon in place, and we have also our A3 synthon in place. Now a Michael type reaction can take place where the combination will be between these two carbons, and I will end up with something which resembles a 1,5 difunctional compound. And now a cyclocondensation will take place, where I will have a 1,4 dihydropyridine derivative, which is a resonance stabilized vinylogous amide kind of thing. And then I will remove these two hydrogens from here. So I will have to do a final oxidation step, which is a dehydrogenation or oxidation or aromatization, which can be done with sulfur, heating with sulfur, so that I get my corresponding pyridine derivative. So this part is coming from one of the active methylene, that part is coming from one of the active methylene, and that part is coming from nitrogen ammonia, and that part is coming from the aldehyde that we have using. The color codes indicate that which part of this ring system has come from which of the starting materials. Obviously this is one of the possibilities. It is possible that other sequence of reactions are happening. So it may so happen that maybe this enamine will condense with the aldehyde and then it will condense with the other active methylene. But those are possibilities which cannot be ruled out, but this seems plausible enough. The mechanism of enamine formation and the mechanism of the aldol type of reaction, which is a Knoevenagel reaction leading to the enone, is also outlined here. So we have some examples where we have used two molecules of ethyl acetate condensing with formaldehyde in presence of ammonia. Ethanol is the reaction medium. When refluxed, it gives you this is the so-called Hantzsch dihydropyridine, and this is typically oxidized with HNO3 to give you this compound, which loses the two carboethoxy groups when hydrolyzed with calcium hydroxide and then further heated, so that a decarboxylation takes place of the resulting carboxylic acids to get the 2,6-dimethylpyridine. Okay. If I am to use a different aldehyde like a PHCH2CHO with the same reaction combination, then instead of couple of hydrogens, I will have one hydrogen here and a PHCH2 group here. Now, from this, when we oxidize with HNO3, we end up with the departure of this hydrogen and this hydrogen. But when this is subjected to the diazotization condition, NaNO2 acetic acid at room temperature, then we lose this one and this hydrogen. So we have only hydrogen here when treated with NaNO2 acetic acid, and we have only the CH2PH here when the HNO3 oxidation is taken place. Before we go into the details, let's also look into the use of the acetyl acetone. When you take acetyl acetone and acetaldehyde in presence of ammonia, so you are going to end up with a methyl group here, and that's also when you are doing the reaction in NaNO2 acetic acid at room temperature. When you had the benzyl group, treatment of NaNO2 acetic acid resulted in the loss of the benzyl group, but when you have methyl, the same treatment loses only the hydrogen. The methyl or the alkyl groups remains here. And obviously, as you have started from the COMe groups here, because you have taken the acetyl acetone, you are also going to end up with the two ketomethyl groups. Okay, so what is happening? In this case, what is happening? We are doing the two workups, and their outcome is completely different. So basically, when you do a NaNO2 acetic acid treatment, what you are looking to do is that you are nitrosetting this nitrogen, and this nitrosation will endow this nitrogen associated with a goodish kind of leaving group. So one of the two things may happen: either H plus can leave and NO minus can leave, or R plus can leave and NO minus can leave. R plus can only leave when R plus is able to sustain the positive charge, which is the case when you have CH2PH. Therefore, a benzylic carbocation will leave, and it will eventually be consumed by any nucleophile present in the reaction medium. But because this is a relatively stable carbocation, instead of H plus, R plus has the tendency of leaving. But when R is equal to methyl, then this type of reaction cannot take place and methyl is retained. And when you are doing the reaction not in presence of NaNO2 acetic acid but in presence of nitric acid, it is a simple oxidation, it is a simple dehydrogenation, and the CH2PH group is retained. Okay, so after Hantzsch pyridine synthesis, there is another method which avoids the final oxidation step. Recall, in the very first retrosynthetic analysis, we put one hydrogen here and one hydrogen here. Therefore, it became imperative for us to carry out a final oxidation reaction, because the novenagal condensation followed by the enamine formation followed by the combination of the enamine and the enone leading to the 1,5-difunctional compound and cyclization led to a dihydropyridine. But if we think that instead of adding H here, let us add one H here and add one OH here. So we are basically ending up with a different revised target molecule, and that carbon that oxidation number is actually 2 units higher than the oxidation number of here, because if one hydrogen is associated here, this carbon has an oxidation number of -1, and because it is now OH, it is actually +1. So the oxidation number is actually 2 units higher at this carbon. Therefore, with this strategy, we will be having a spontaneous dehydration reaction from this intermediate to the final pyridine nucleus, and we can avoid the final oxidation step if we think in this term, and then add one H here, one OH here, and then go on carrying out the same things. You will end up with the same enamine, and instead of alpha beta unsaturated carbonyl compound, because you have an oxygen substituent here, you will not have a double bond here. Instead, you will have a 1,3 electrophile, but this carbon's oxidation number will be different. It will be a 1,3 dicarbonyl, which is again a A3 synthon. So 1,3 dicarbonyl synthesis, we know that we can go for the Claisen reaction, and again the probable mechanism may be something like where enamine is reacting with one of the two possible carbonyl compounds, giving rise to 1,5-difunctionalized compound, which is cyclized, and then loses one water molecule from here and one water molecule from here, so that we can end up with our desired pyridine nucleus, where the final oxidation step is made redundant. So for example, we have taken with ethyl acetate and then treated with ammonia under suitable condition, so that we get the corresponding enamine, and that enamine reacts with acetyl acetone. Because acetyl acetone has the two carbonyls equivalent, it does not matter which of the carbonyls is first attacked. Because these two are equivalent, you are always going to end up with this product. But if they are different, so if you say unsymmetrical 1,3-dicarbonyl compound, then it may so happen that the nitrogen attacks this carbonyl first, so you end up with that one, where R2 is at C2 and R1 is at C4. Or it could happen that it is attacking the R carbonyl associated with R1. Then in that case, you will get R1 at this position and R2 at that position. R1 is at C2 and R2 is at C4. These two are obviously regioisomers. When we are using this compound, with this particular compound, it is always this compound which is being formed. So that's basically the 1,4 addition being promoted. The 1,2 addition being promoted at the aldehyde carbon instead of the ketone. So in that case, you will have the hydrogen installed at the C4 and the R installed at the C2, because presumably the reaction proceeds via the addition of the enamine through the carbon of the enamine onto one of the two carbonyl carbon of the A3 synthon or 3-dicarbonyl, and between those two carbonyl carbons, the one which is more electrophilic is more likely to undergo this nucleophilic attack, because aldehydes are much more electrophilic than the corresponding ketones. It is the association of that carbon with that carbon which takes place first, and automatically the position of the R is fixed at C2 and the hydrogen is fixed at C4. Okay, so these two syntheses we have in our syllabus for pyridine nucleus. Let us tackle the question of quinolines. The most famous synthesis of quinoline that we have is the Skraup quinoline synthesis. Let us do the retrosynthetic analysis. Add couple of hydrogens here, one hydrogen here and one hydrogen here. So basically you need to do a oxidation. Once you have this 1,2-dihydroquinoline as your revised starting material, then add the molecule of OH, the elements of water, that is one OH fragment here and one H fragment here. So that gives you an alcohol. Now do a HOCC reaction by cleaving this bond. So what you have is an aldehyde which is attached with this nitrogen, and this part is obviously coming from an aniline derivative. So this is a 1,2,3,1,3-diex compound. Now disconnect the CN bond, because CN bond formation is relatively easy, and therefore you have a plus here and you have a minus on the nitrogen. So obviously you are looking to get a A3 synthon, and in this case it will be alpha beta unsaturated aldehyde or enal, and this one is obviously D2 synthon, because nitrogen is nucleophilic as well as its ortho position is also nucleophilic. So this serves as your aniline, which is the D2 synthon. Thus we have the Skraup quinoline synthesis, where glycerol is used as a precursor of this enal, that is the acrolein. The reaction is done in presence of sulfuric acid in the nitrobenzene solvent. Ferrous sulfate is used for a special purpose, and this reaction is actually very vigorous and it's kind of difficult to control. So there are many steps. The very first step is we think of dehydration or rearrangement of the glycerol into the corresponding acrolein. So what happens is, first if this becomes protonated, it leaves a secondary carbocation may form, or maybe the rearrangement is spontaneous, concerted. So this hydrogen leaves and this oxygen stabilizes this positively polarized carbon. So this is a pinacol-pinacolone rearrangement, where we get a beta hydroxycarbonyl compound, which under this reaction condition immediately dehydrates to the corresponding acrolein. The acrolein undergoes the nucleophilic attack from nitrogen. So this nitrogen attacks this carbonyl, beta carbon. So it's a Michael type 1,4 conjugate addition, where the nitrogen combines with the beta carbon, and ultimately tautomerization gives you the corresponding aldehyde derivative, which undergoes aromatic electrophilic substitution and eventually a dehydration into the 1,2-dihydroquinoline. Now this 1,2-dihydroquinoline is oxidized to the corresponding quinoline, so it gains aromaticity. And the oxidizing agent is a little bit surprising. It is the nitrobenzene itself which is present in the reaction medium, and it oxidizes the 1,2-dihydroquinoline into the quinoline and gets itself reduced to the corresponding aniline. So the role of nitrobenzene is as a solvent, first of all, and secondly, it is also the oxidizing agent, and this aniline is recycled here. So nitrobenzene plays a lot of role. The reaction is actually very difficult to carry out. The principal difficulty is the violence with which it happens, and to moderate the reaction, otherwise it is an extremely vigorous reaction. To moderate its vigorousness, ferrous sulfate is acting as a moderator. But in majority of cases, the reaction gets beyond of control and the starting material or the product is lost through condenser because it refluxes very, very violently. Then we have the Doebner-von Miller's generalization of Skraup quinoline synthesis, where they have used a different starting precursor for the enal. They have used acetaldehyde. The reaction is done in HCl, and this acetaldehyde is actually the precursor of the crotonaldehyde. So 2 molecules of acetaldehyde undergoes acid catalyzed aldol condensation to give you crotonaldehyde. Again, the nitrogen attacks at the beta carbon of the crotonaldehyde, and then subsequently the aromatic electrophilic substitution takes place, followed by dehydration to give you the 1,2-dihydroquinoline derivative. Now this time you have a methyl here because you have not started from acryldehyde, you have started from crotonaldehyde, so you have a methyl here. So you need to oxidize it, and that oxidation is possibly carried out by a Schiff base or a imine which is formed from aniline and acetaldehyde. Because acetaldehyde is present in excess, there could be something like this, and this gets reduced itself into a secondary amine, N-phenyl N-ethyl amine, and this 1,2-dihydro quinoline derivative aromatizes to the corresponding 2-methyl quinoline. So that's basically, we can say that this is a reductive amination of acetaldehyde, where acetaldehyde C double bonded O is replaced by N double bonded C of the aniline, and then this C N double bond linkage is reduced by the couple of hydrogens that are coming from here, and we get a secondary amine. Now if you have alpha beta unsaturated carbonyl directly added into the reaction mixture, you can also do that. So if you take methyl vinyl ketone, then nitrogen will establish its linkage with this one, and this orthocarbon will establish its linkage with that one. Therefore you will end up with a methyl here. And if you take the crotonaldehyde and if you employ something which is different from aniline, then these two OMe groups will end up at these two positions, and obviously nitrogen will attach with that carbon and the orthocarbon will attach with that carbon. So the key to the success of this reaction is to understand that the nitrogen lone pair is encouraged for the Michael type addition, where the beta carbon of the enone or enal that you have is reacting here. Now there are modifications of this method and there are extensions of this method. Just as the Hantzsch pyridine synthesis was modified by changing the oxidation number at the revised target so that the final oxidation could be avoided, instead of alpha beta unsaturated carbonyl we used a 1,3-dicarbonyl. The same strategy you can adopt here. For the Skraup synthesis, you have basically a ranine amine which is a D2 and a A3. Now A3 is represented in Skraup synthesis by a alpha beta unsaturated carbonyl, and so in the Doebner-von Miller's modification. But what about if you take not the carbon-carbon double bond here, but a carbon-oxygen double bond, so a 1,3-dicarbonyl. So basically you are altering the oxidation number of this carbon again. So that carbon is again its oxidation number is 3 units higher, and in this case the oxidation number is 1 unit higher. So you have altered the oxidation number in such a way that the final oxidation step is not required. All you need is basically a dehydration. So 1,3-dicarbonyl if is present, then aryl amine will have the choice of attacking either this carbon or that carbon. So think of maybe this is attacking this carbon, so enamine formation is taking place, basically like an enamine formation. So it attacks here, it forms a hemiaminal, then this double bond is presented here, and this double bond is conjugated all throughout. Therefore the double bond the dehydration is very, very, very facile. Then you have the intramolecular aromatic electrophilic substitution, where this position attacks here and this becomes the alcohol, and then you lose the H and OH, and so that you get the aromaticity. No oxidation is therefore required. So if you take symmetrical molecules like acetyl acetone, you will have finally the two methyl groups installed here, and when these two are mixed together and heated, the enamine formation is spontaneous, and then the aromatic electrophilic substitution is promoted by the presence of the concentrated sulfuric acid. The OMEs that are present here, they encourage this position to attack that one, because it is para with respect to one of the OMEs and ortho with respect to the nitrogen. Now, regioselectivity issues may crop up if we are using unsymmetrical 1,3 dicarbonyls like ethyl acetoacetate. Now, if you do the reaction at 140 degrees centigrade for 3 hours, then it is the ester group which reacts with the NH2 to form this compound. Ultimately, intramolecular aromatic electrolytic substitution by polyphosphoric acid and subsequent dehydration will establish this linkage, which means we will have a double bonded O here and the methyl group here, the tautomer of which is this one. So hydroxy at 2 position and methyl at 4 position. But if the same reaction is done on at room temperature for 5 days, then the enamine formation takes place. This time we had an amide formation, and this time we have enamine formation. So it is this carbon which is more electrophilic and undergoes this reaction. Because this is at room temperature, it is the kinetic control, so that forms faster. And then if this amide or this enamine is treated with Doubtherm, then at 260 degrees centigrade, it's a 6 electron electrocyclic ring closing, which the mechanism of which is not underlined here or not delineated here. It undergoes the 6 electron electrocyclic ring closing to give you this compound, where the hydroxy or the C double bonded O is at the C4 and the methyl is at the C2. So again, just like in this case you had the opportunity of the mixture of regioisomers, here you also have mixture of regioisomers. One is the kinetically controlled product. It is the more electrophilic carbonyl which undergoes this reaction, but at elevated temperature the thermodynamic control takes place, and thermodynamic control means that the more electrophilic but more stable keto linkage is retained, corresponding to the rather than the ester linkage. So here is the keto linkage retained, and here you have the ester linkage retained, and the ester linkage is also cross conjugated here, and the keto linkage does not suffer from any sort of cross conjugation here. So it is the thermodynamically controlled product and it is the kinetically controlled product. By varying the reaction temperatures, you can encourage the formation of one over the other. Finally, we move on to the synthesis of isoquinolines. These are the Bischler-Napieralski's method. The retrosynthetic analysis is a little bit different. So here we have the nitrogen removed from the ring. So add one hydrogen here and one hydrogen here. So basically you are doing 1, 2, 3, 4, a 3,4 dihydro isoquinoline, and then add the OH here and the hydrogen here, so that you have a HOC and HOCC or HOCN type of linkage. Instead of HOCN, you do the HOCC. So you disconnect here. So you get amide linkage here in HCOCH3, and then you expect that this carbon and that carbon will close down the ring. And this is an amide, therefore you can directly disconnect the CN linkage to reveal the acyl agent, which could be acetic anhydride or a acyl chloride, and this is a alpha, this is a alpha beta. So this is a beta aryl amine. This is the alpha carbon and that is the beta carbon. So it is a beta aryl amine. So beta aryl ethylamine. Beta aryl ethylamine. Beta aryl ethylamine, it could be synthesized from the corresponding ArCH2CN, which is synthesized from the ArCH2Br, which is synthesized from the ArCH3 by allylic halogenation or benzylic bromination, followed by displacement with sodium cyanide in DMF, followed by reduction of the cyanide compound with lithium aluminum hydride or a horde of reducing agents. So this beta-aryl ethylamine is easily accessible, and then you acylate this nitrogen to COR, and then you do the POCl3 heat treatment so that intramolecular aromatic electrophilic substitution takes place, and this oxygen is taken away by the POCl3. So that's kind of should remind you of the Vilsmeier-Hack formulation, and all that remains is to dehydrogenate these two positions by heating this with palladium carbon or sulfur or selenium, so that you get your isoquinoline derivative. The mechanism of the dehydration is kind of disputed, or I could say that there are different types of mechanism where imine ester linkage establishment can account for it, or it could be like a Vilsmeier reaction where this nitrilium ion is involved, and which is further captured by the benzene ring to give you the corresponding 1,2-dihydroisoquinoline, etc., etc. So any of this is acceptable. And suppose you have substituents present in the ring. So because this is the electrophilic attack from the ring to the nitrilium ion, or could be the iminoester linkage, whatever, it's an electrophilic attack onto the ring. So if you have electron releasing groups, the reaction is very facile, and you see that the reaction temperature is only 100 degrees centigrade, the yield is 88 degrees centigrade, yield is 88%. On the other hand, if you have presence of electron withdrawing groups, despite this being a meta position, this is an electron withdrawing group, therefore the reaction is very difficult to control or carry out. So it's a 210 degrees centigrade with only 5% returning yield. So the synthesis of 1-methyl isoquinoline is established here. So you can understand that this should be coming from a MECO group, that should be coming from the beta-phenyl ethylamine. So we do that with MECOCl in pyridine. So we have the amide linkage established, and then P2O5 POCl3 heat, and then we have the ring closing reaction, the intramolecular aromatic electrophilic substitution, followed by dehydrogenation. Then we have the Pictet-Gams modification, again which does away with the oxidation. So basically you, instead of this hydrogens here, you alter the oxidation number of this carbon by putting a OH here. Now this could be coming from obviously a carbonyl compound, so you need to reduce that. The amide cannot be reduced or should not be reduced, chemoselective reduction will be required, and amides are notoriously difficult to reduce because of the resonance stabilization. On the other hand, this is a aryl ketone, so this should be theoretically much more vulnerable to reduction. So you could use chemoselective reducing agents to obtain this reduction product. And when you do the reaction with POCl3 CaCl3, it's obviously it has an opportunity of dehydration. Instead of any hydrogen, it has one OH here, and therefore one hydrogen and one OH can leave, is installing a double bond here, and so obviously there is a there you can avoid the final oxidation or the dehydrogenation step, which is required in the normal Bischler-Napieralski. So this is the Pictet-Gams, and the question is, how can you get that? So this is obtainable from this acylation of this amino ketone, which can be obtained by the reduction of the corresponding oxime. The tautomeric form of this oxime is this nitroso, and 1,2-dix disconnection will give you a corresponding ketomethyl derivative, ketomethyl aryl ketone, where you have only access to this alpha carbon, which is nitrosated, and this nitrosated derivative can undergo tautomerization to give you the corresponding oxime. This oxime can be reduced to the corresponding amide. Amide can be acylated to the corresponding the amine can be acylated. The reduction will give you the amine. The amine or the ketoamine will give rise to the amide, and this amide can undergo further reduction to achieve this hydroxyl group at C4, and then you have the ring cyclization. So this will require a careful control of reduction of this one in presence of this carbonyl, reduction of that one in presence of this carbonyl. So not a very easy method to go about, but it is possible, and in line with the modifications that we have already seen for the synthesis of pyridines, the modification of the Hantzsch method, and the synthesis of quinolines, the Combes method, which modifies the Skraup's method. So worth noting, the Pictet-Gams modification is also worth noting. So this much for our syllabus, and I hope that these lectures have been useful to you, and I thank you for your patience. I will be seeing you whenever it is in the next one.